afternoon. Yeah, distinguished scientists and engineers. So my name is Seokju Bae in Hanyang University. Currently, I am president of Korea PHM Society. Yeah. It's my honor to welcome all of you. Join us for the 2023 BrainLink X Day talk concert. The topic is PHM. PHM is the prognostic and health management and reliability engineering for fault diagnosis and predictive maintenance of battery and manufacturing equipment. And first, we'll have a welcome remarks from President Tae-sik Lee of Corpus, who provided us with this excellent opportunity. Yeah, welcome. Yeah, President Tae-sik Lee. Yeah.
Welcome all speakers all over the world, Hong Kong to the America, and the other guests welcome here. Welcome all of you to the 2023 BrainLink X Lab Day. I will call BXL, not the BTS, but the BXL. Talk concert titled PHM and Reliability Engineering for Fault Diagnostic and Predictive Maintenance of Batteries and Manufacturing Equipment. I appreciate the organizer, Professor Seokju Bae from Hanyang University. It's a very good university. I'm from there too. And Professor Kwak-rung Chui from Virginia Tech for successfully orchestrating today's X Lab Day. Thank you so much for all the speakers, panelists, and chairs for their invaluable contribution. This is very important because our R&D budget is $27 billion, and that 10% will be the global cooperation. So you're expert for the batteries. With him, you will have another chance that we will spend the 1/10. That means $2.7 billion for global collaboration. So apparently battery is very important. So you may have very good condition next year. The Korean Federation of Science and Technology Societies, I call COST, F is a silence, so much easier pronounced, so COST, has 608 members organization from industry, academia, and research, with 13 regional federations and 19 overseas Korean Scientists and Engineer Association. This extensive network has paved the way for the development of the BXL, and we remain committed to spearheading networks for international cooperation in science and technology within Korea. The BXL was started last year with a view to establishing research network at the global level while fostering technology exchanges among eminent scholars, seniors, early career scientists and engineers from home and abroad. In 2022, the first project hosted a total of 14 technology exchange meetings with 449 participants actively engaging in the event. This event was closed, but actually this year event also closed, but we make the event today like today. So we will make the broadcasting, so you can give the more knowledge than more people, not only the 30 or 40 specialists, but also graduate students and all the other researchers. So this is a very important event today. This year, the BXL will host 10 technology exchange meetings in Gangwon Province, Korea, covering 12 national strategic technologies, Furthermore, we have arranged a special talk concert with the speaker of the BXL project, aiming to extend the knowledge sharing platform beyond the in-depth exchange reserved for selected group of experts. As you know, well, secondary batteries have captured global attention and are now recognized as a key technology in the fourth industrial revolution. Considering their widespread application in areas integral to our daily lives, such as electric vehicles and portable electronic devices, I believe that it is crucial for us to foster a deeper interest in secondary batteries. I'm sure that this BXL serves as a dynamic platform for robust discussions to explore insightful ideas that can enhance the performance and safety of secondary batteries. Furthermore, I expect that this project will provide an opportunity to facilitate global research exchanges and cooperation between Korea and the rest of the world, as I explained. I hope that all of you find this event to be a valuable networking opportunity. I appreciate your participation in this meeting. I wish you all the best in the future endeavors. Thank you so much. Welcome again.
Thank you first. Welcome remarks to President Tessin Lee. Yeah. This X-Day, BrainLink X-Day, the top constant topic is PHM reliability for battery and manufacturing equipment. Nowadays, the battery industry very important in Korea as well as any other countries. So I hope we can exchange many ideas together. With this open talk concert, and we'll have a small conference in Pyeongchang from tomorrow, but many people cannot join the conference. So the reason why I give this open talk is to deliver any idea to general people who are interested in this topic. So I hope you enjoy this open concert, not BTS concert, but yeah, this is a very nice concert. Yeah. Now let's watch a video introducing BrainLink. Okay.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. In 2022, the inaugural X Lab Day saw a total of 14 meetings across various technical fields. Altogether, 449 individuals participated, comprising 70 from overseas and 379 from Korea, all aiming to build a stronger network in Korea and abroad. This year, for our 2023 X-Lab Day, we have the honor of having Xingteng Yao, professor at Tsinghua University and a Fields Medal winner, Philip Kim, a globally renowned professor at Harvard University, known for his research in graphene, Yunsung Huang, professor at Stanford University and Hoam Award winner, and Humboldt Research Award winner, Zhigang Suo, professor at Harvard University, leading discourses of their respected fields. This year, the discussions will span 12 national strategic technology fields pivotal to Korea's advancement, including quantum mechanics, nuclear technology, and AI. The event will see the participation of 30 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. The focus of X-Lab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each X-Lab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST supports the reinforcement and expansion of the networks established through X-Lab Day. COAST, the organizer of X-Lab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the 4th Industrial Revolution, where science and technology spearhead groundbreaking challenges, COAST remains dedicated to its role as a facilitator of scientific and technological innovations. In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink X-Lab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making X-Lab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink X-Lab Day.
Again, I give my appreciation giving this nice opportunity. Yeah. First, let me introduce the speakers. First, Professor Kwang-Nung Choi in Virginia Tech, and second, Jan Shi and Georgia Tech, and Tony Ng, Professor Tony Ng, and Bentley University, and Mano Lee, and Hong Kong Educational University. And first speaker is Professor Kwang-Nung Choi. Why don't you come here and you can give your speech? Maybe 15 or 20 minutes will be okay. Yeah. So yeah, just come here and maybe. Is there any CV? Yeah, maybe. Yeah. Let me introduce the Professor Kwang-Nung Choi, Graduate Department of Industry and System Engineering, Virginia Tech. His topic is personalized health management with sensor technology and data analytics. Yeah. Let me welcome the Professor Kwang Rung-chi. Yeah.
Thank you, Professor Bae, and thank you, President. So I'm really honored to be here and share with you some of my research on this topic. But before I move on, I also want to thank you for the opportunity for being one of the organizers for this event. But I must say, though, as the Professor Bae has done most of the work, I am really just helping and supporting Professor Bae. So I really want to thank Professor Bae for putting this together. And today's our focus, the topic of this PHM is on batteries and manufacturing equipment. But I will talk about the battery and the equipment in tomorrow's 3 days event. Today, I actually will share with you, actually, it's a little a different twist on this PHM. The theory and all these ideas are the same, but the application now in PHM has been extended from equipment, machines, engineering system to human systems. So that's what I wanted to share with you. I have been doing research on many different applications, including manufacturing equipment and batteries, transportation equipment, etc. And in the last number of years, we are extending the application from this system to human health systems, which actually is a very important topic as well. So with that, I will share with you with 3 parts of that. And first, I will give you, again, all these PHM things that were really motivated by the advancement of the technology. So this advancement include advancement of the sensor technology, where then is nowadays we have developed very sophisticated sensors, which are a lot more much less costly, and so that we could apply or install the sensor into many systems, okay, including, a machine and equipment, and including human. So then what you are doing right now with your Apple Watch or some other things you are wearing, then we could use those sensor technology to monitor, okay, the health condition of the humans or whatever other system you are doing. So this is the new direction because of the advancement of the technology. So I have been involved in this type of research. So in addition to the sensor technology, there are also advancement on this computation, machine learning, statistical learning methods, okay, data science, data analytics method, predictive analytics method. So those are another advancement. So combining the data collected by this sensor technology as well as these advanced modeling methods, okay, in machine learning, artificial intelligence and all that, and then we're able to do a lot more than what we were able to do in the past. So I have been involved in a number of these topics in terms of different applications, including healthcare, public health. So we refer to healthcare and public health. Healthcare referring to your human body health, and public health refers to that society, the community health. So the example will be, for public health, will be the latest COVID pandemic or some other flu or some other, I guess, the swine flu and some other new infectious disease. And then human health, of course, includes any kind of disease you have, or even the aging of a human body and all that. So there are a lot of advancement of this in this area of research that I would like to, I have been doing in the past, but today I will only share just some of them, okay? And so these are the 4 topics we have been involved in terms of the human health, okay, as well as the society, public health, monitoring, and surveillance, okay? And so this is the healthcare and public health surveillance that for this kind of research we have been doing at least for more than 10 years in the past, since the SARS and later on the swine flu and MERS, and the latest is the COVID. Okay, so this is the area of research we have been doing in terms of collecting data with the sensor and applying the method for monitoring. Okay, and so there are different types of health surveillance, including, healthcare, public health, or syndromic surveillance. Will be referring to this infectious disease. And a good example that we use for this area is if you go to search in the web, then you find out something called Google flu. Okay, Google flu is a good example about this type of monitoring and surveillance. Okay, and so what they have done is that they make use of the data collected from the internet search and try to predict, okay, the occurrence of the influenza or the flu each year. Okay, so that's important for them to know. But if they don't make use of this search engine data from the internet, it will be much slower for them to detect if there is an outbreak of the influenza. So every year, just like COVID, okay, that if right now you have very fast tests for COVID, but before we have this fast test, they don't know if there's a COVID in somewhere. So if you wait until this test to be developed, then it may be too late. So this type of research is really to try to make use of other type of data to detect it. Okay, and then from there you could develop other type of modeling. Okay, and you could use a simulation to find out once you detect the disease, then you will find out how the disease was spreading over time. Okay, so this is some of the work we have done. This was the swine flu outbreak back then, and how they were being developed. These are the tools we have used. They're called simulation tools, which will be used to see how the disease was spreading. Okay, these same tools were being applied to COVID. Okay, which the latest one, that the simulation tool was developed in Virginia Tech, the campus where we developed the tool to find out how the disease was spreading within the campus, so that we developed the method to manage it and reduce the impact of it. And so this other application will be from the public health to the human health care, which are referring to the hospital or clinic and the environment where the same tool can be applied. And so again, you could develop simulation models for simulating how in the emergency room, how operations were being carried out. So the same method, we have done similar thing in the healthcare sector. So the methodology and the modeling tools are very similar, but the applications are different. And finally, will be what we call the individual health management or personalized health management, which is another very hot topic we are doing. Okay, that will be related to, we put sensor in your body to collect data about your body's reaction, including the Apple Watch, including some other sensor we mount on your body to collect the data, including your heartbeat, some other activity you're doing. From collecting those data, we're able to do the modeling to find out your health condition, and then we will be able to tell that if some problem is happening in your health, so that we could react to them before the problem come out. So this is the idea of this area of research. And now with this high-level introduction, I will have very quickly go through these 2 topics, but because we have only short sharing today, then I won't talk about any detail. The first one is something I already talked about, so I will be very brief. It's about public health. The second one will be about the personal monitoring. These are the 2 topics I will be focusing on. Okay, the first topic I already talked about, that is the health we call that healthcare and public health surveillance. It ranges from monitoring the development of this disease, could be chronic disease, could be infectious disease, okay, ranging to the pandemic, okay, so that's why you could have chronic disease, you could have natural outbreaks. The latest one was the COVID. So all these different type of monitoring, you could be applying the same similar type of tools, okay? And for different type of application, your objective could be different, okay? And this is the example we just talked about is the Google flu, okay? So if you are able to detect and find out the outbreak much earlier, it does not have to be much earlier, 1 week or 2 weeks earlier, then the society or the community will be able to manage the problem much better, okay? You wait until just 1 week or 2 weeks later, then the problem could have been much worse, okay? And these are the data they're collecting. These are different examples we won't have time to talk about. And this is the mathematical model, okay, of the monitoring method. And these are some real data set we have worked on during our research. And we developed methods which are very effective, okay, that you're able to detect the red marks are the actual outbreak. The blue, the green, and the yellow are the background. So our objective is to detect the red one from this background. So depending on the type of application, sometimes it could be very challenging. Just like the blue background, you detect the red. The red does not look any different from the blue. But if you're using sophisticated modeling, you're able to detect this red from the blue, okay? So that's the type of method that has to be very robust, and also it has to apply to many different type of problems. And these are, in addition to just what we call it, the temporal monitoring, is over time. You want to find out what time they happen. We also have spatial temporal, that is, in addition to finding out what time this outbreak takes place, you also want to find out where it will take place, okay? Like in Korea, you have different cities. So when there's some kind of infectious disease outbreak, we want to find out which location has the biggest problem. So that's called spatial temporal surveillance. And this is the mathematical model for that, for the detail of the method. As we mentioned, once you detect the problem, we also want to find out where this disease was spreading. So we develop a simulation model to find out how the disease is being spread in the community, in the city, or in the entire country, even in the world, okay, depending on their spread. So this is actually the simulation model I mentioned earlier, that we started the research back then in swine flu, bird flu, 15 years ago, but now the same type of model need to be modified for COVID. So this is the new model we developed for COVID application in the campus of Virginia Tech. So that is a very effective tool for you to learn about the spreading of the COVID within the campus, as well as to predict how many people are dying and how many people were getting infected. And so we develop different type of method and compare them. These are the detail of the research approach. So I will spend another 5 minutes to talk about the second topic. So the first topic was in public health surveillance. The second topic actually is called personalized health monitoring, which is referring to how do you monitor the health of an individual. So this actually is a very hot topic right now. It's called personalized health monitoring and management, which is an extension of the PHM from the equipment to the human health, okay? Again, it's because of the advancement of the technology, okay, including everyone is wearing maybe not just Apple Watch, but Samsung Watch, okay, that they are collecting data about your daily activity. They're collecting data about your heartbeat and some other things, okay, during the day. So if we are collecting this data, well, we'll be able to tell what your health condition is, and they could predict if you have any health problem, and then they will come up with a way to correct the problem if that happens. So that is really the new trend right now, and the idea is not a brand new idea, but it was not possible to make it work in the past. But now, because of the advancement of the technology, it is possible. Okay, so the idea is from the traditional corrective health care. Okay, in the old days, you do corrective health care, or even right now, you do corrective health care. If you're sick, you go to the doctor. Okay, but and then also you do an annual checkup every year. Okay, so those are the old traditional method. The new method is you wear the Apple Watch or you wear some other sensor when you are sick. Let's say you have a heart problem. You could wear a special vest to monitor your body so that they can monitor your heart disease, how they were developing. So there are all kind of potential. Okay, and the idea for this type of approach is that we wanted to detect the problem before it happens, which is a lot more effective, okay? In particular for older adults. For young people, it's not as important. Let's say when you are sick, then you could go to the doctor. You will recover very early. For older adults, if you're sick or if you have a problem, you don't detect it early, once it happens, the consequence is very big. So for our application actually, for the moment, is focused on the older adult because the impact of detecting the problem and correcting the problem is very big. If we were able to do it, we could significantly save the healthcare cost. Because when an older adult falls down, then they could break their bone, they could be sent to the hospital. It takes maybe a few months for them to recover. So the consequence is so big that we wanted to detect the problem before they happen. Okay, so that's why the leverage is much bigger for older adults for the moment. But that doesn't mean that you could not apply to younger adults and some other people. Okay, and this is interdisciplinary research. We have worked on interdisciplinary proposal on this. This research required expertise from different area, okay, ranging and all that. And then there are different type of device you have to develop, and you need the sensor system, devising, and etc. You also need to develop the predictive model. You need to develop the science, and finally you have to implement them using the software system. Okay, these are just some examples. I mentioned about your Apple Watch, some others, but they are not limited to this. There are many, many other sensor devices you could apply for monitoring the human personal health. So these are various ones we have to develop. Here's the general concept. So the current project we have right now, we have something called a smart self-assessment and monitoring system for gauge and balance. Gauge and balance is about an older adult, how strong and how healthy they are when they walk and balance, okay? And that is a very big problem for the older adults. So we're developing this system by making use of the sensor, the data analytics method, so that we will be able to detect, we will be able to predict the fall risk of an older adult. That means that we could predict what is the chance that an older adult will fall in the next 1 month, in the next 2 months, etc. So if you are able to predict that fall risk, then you will be able to come up with some strategy to reduce the risk, okay, and correct the problem before it happens. So these are the sensor equipment we develop. Okay, it is some kind of vibration sensor, inertia sensor that we mount on their waist so that we could collect data about. And we could use other type of device such as Kinect, which could also be used, okay, to detect the motion of the human. And this is the modeling detail of how we were doing it. You have to run experiment in collecting data from different type of adults with different level of risk so that you could develop some kind of risk model. So once you develop an accurate risk model, so in the future, when an older adult, they could wear the sensor, do some standard exercise, then you will be able to evaluate the risk of this older adult. So that if the older adult does this every other day, you collect data, you could do it daily, every other day, or weekly, depending on how healthy the older adult is. And then once you collect the data, so you could do this at home without the medical expert, and so that we could monitor the fall risk and the health condition of the older adult. Then if something goes wrong, then you will recommend some kind of corrective action. Could be educational program, could be sending the older adult to see the doctors, etc. So we want to correct the problem before the happens. We will continue to monitor the problem, etc. Okay. So with that, and that is the application of this healthcare for the personalized monitoring and the public health. I'll stop here, and we could answer any question you may have right now or later. Yes.
If you have any question, just we can have just one question. Maybe we have the panel discussion after all talk are given. So maybe panel discussion we can discuss the more details. Okay. Thank you for Professor Kwang-Lun Chui. Yeah, giving excellent presentation. Professor Chui gave a speech on healthcare for person, but the PHM for persons are very procedure very similar to PHM for battery and equipment. So, I think this is more insightful to understand the PHM. Yeah. Okay. Also, I give my congratulations for Professor Kwang-Lun Chui was selected as most highly cited researcher in cross-field engineering area. So congratulations, yeah, recently, yeah. Next speech, Professor Jae-Jun and Georgia Tae. It's my honor to invite Professor Jan Si. He's very excellent scholar in industrial engineering and mechanical engineering. He'll give a talk and quality and reliability integration in multi-stage manufacturing process. Welcome to Professor Jansi. Yeah.
Thank you, Professor Bei. It's really a pleasure and honor to come here to give this talk. In this talk, we're really talking about deliver two messages. One is quality and reliability should study together. It cannot be separated. And the second one is in multi-stage manufacturing process, quality and reliability integration has some unique aspects, unique problems. So in this one, I will first talk about what's multi-stage manufacturing process, what are the R&D challenges, and then I focus on integration of quality reliability and QR chain, quality reliability chain effects in multi-stage manufacturing process, and then give a summary. So what's a multi-stage manufacturing process? I say almost all manufacturing systems are multi-stage. For car assembly, there are about more than 100 stations assemble a car from pieces, stamping parts to final product. Engine head goes through 24 machining stations from casting parts to an engine head. And the 3D printing layer by layer is also multi-stage manufacturing. For sure, battery manufacturing is a multi-stage manufacturing system. So for multi-stage system, what are the common issues or challenges? So you can see from this list. First, if something wrong in one station, this quality problems will propagate to the final product. So in other words, there's a variation and the variation propagation modeling issue from detail stage to final product. Another one is the tolerance synthesis. In other words, the final product has certain quality expectation, how to allocate the tolerance to each individual parts in each station, and also assign tolerance for the tooling in each station. So the tolerance synthesis. Another thing, the root cause diagnosis. If something wrong in the final product in terms of quality, in which station, which parts give us trouble. So how to find the root cause. And then distributed sensing. In other words, there are multiple stations, multiple parts, in which station measure which features of the product or tooling conditions. So how to use minimal number of sensors to make system diagnosable. So that's a distributed sensing problem. Critical station identification. In other words, there are multiple stations. For sure, one station gives more trouble than others. So how to identify this? And automatic compensation. In other words, in the middle of certain stage, the product already not perfect, some errors there. Can we do something downstream to make the product better in the final product? So all those issues are very important in the multi-stage manufacturing process. So over the years, we have studied this one for different aspects based on different types of sensing, different manufacturing systems. And so for those kind of research, we have generated many publications. And if you go to my website, you can get this, those papers and the presentation available. If you ask the organizer, they can share with you, and you click a link, you can get these milestone papers. So in this talk, I will focus on the stream of variation modeling, which leading to integration of quality and reliability. So what is the SOV, stream of variation? So we understand the manufacturing process in this way. So you can see here the multi-stage manufacturing, and we have N stage. In stage K, there are some quality features already made. Before get in, it's XK minus 1. And after the stage, we have XK. Such quality features go output of this. So if we can model this quality feature by using this system equation, XK minus 1 goes through stage K, become XK, and the UK is the tooling in this stage K, which also impacts the quality XK. And WK is the tolerance of natural variation. So if you can model this kind of relationship from the first to the last station, K equals 1 to N, we can model this quality XK propagation from first station to the last station. And then we have observation equation. In station K, we can measure certain quality features by design the matrix C. So depending on C components, that measure different feature or combination of quality features, which reflect as YK. So by using this equation, if you're familiar with the linear system or system theory, so we can use a lot of concepts to do the optimization, prediction, and so on. So however, there are some fundamental issues by using this one, because in multi-stage manufacturing process, K is a station number, is a limited number. And in control theory, system theory, K is time, go to infinity. So stability, controllability, all those kind of concepts cannot be directly applied to this SOV model. So as a result, we need some fundamental research to do this. So how to interpret this model further? So you can see we have this model, and what are the physical meaning of this? So the XK is the quality features in the K stage. The UK is the tooling conditions. So you can see the tooling condition, which reflected could be a reliability, the machine conditions, impact on the quality XK. And if you think about put a K, put a gamma T. So in other words, UK is not only stage, but also time function. And XK is not only stage K, but also time function. This become a degradation over time, how this variation propagation for each term, if you add the gamma T. This one, how they say the tooling condition UK impact on the quality features. So this model has the potential to link this one. Later on, I say from the quality feature XK or YK can also impact on tooling conditions. That's the quality reliability work together. So how this SOV model can be used for variation reduction or quality improvements. So we can see this one can be used for the modeling, diagnosis, sensor placement, design optimization, tolerancing, and the error propagation compensation. So the very bottom one is the one I like to emphasize, QR chain. I will come back on this. So over the years, we developed this multi-stage manufacturing system. It really covers the design and manufacturing, and we developed a set of methodologies on this topic. And also a company called us DCS in Detroit commercialized this one, developed software called SOVA, Stream of Variation Analyzer, as a product which has been widely used in the automotive aerospace engineering. I'm sure Hyundai or your company, Kia, also use the DCS software, which has modules on our SAOV model. The same thing in the aerospace engineering. So go back, I talk about the quality reliability integration or QR chain effects, which is the second topic I'd like to promote. So why we study the quality reliability integration? There are different reasons. First, we all agree quality and reliability are two important factors in manufacturing process. And typically, the analyze, modeling, optimization of system reliability and quality are normally conducted separately in practice. We have a reliability society, we have quality society, but how these two societies work together and do research together, so it has a very limited activity. And also, quality reliability are interdependent in general, especially in the multi-stage manufacturing systems. So lacking of integrated framework for quantitatively integrated quality and reliability in monitoring and system analysis. This is something the academia should really pay attention and will generate big impacts in industry if quality and reliability can be integrated to do the modeling analysis. So why started work on this topic? That's really motivated by a real case. A major automotive company in US, they developed, they get a new auto plants in over there. And then they use a simulation to do the throughput analysis based on the reliability modeling. The simulation indicates there are 3.5 people for the body shop can maintain the equipments, do all the maintenance. However, once they launch the product, double, 7 people, 8 people full-time still cannot support the maintenance of all the equipments to keep the throughput. The question is, why they spend a lot of money to do the simulation and the results far away, at least a double deviate from the reality. So the VP come to see me, they said, Jan, maybe you can tell us why, what's happening? Why this, we spend so much money and the simulation software is the state of the art. We cannot get the simulation, the design right. So what we found out like this, the system reliability and the downtime analysis, we get people in the plant to see why this downtime, we get all this recorded for the machine downtime. We found out the machine downtime really has two aspects. One is tooling component reliability, like tooling degradation, tooling catastrophic failure, broken. So all this one leading to machine downtime. And all the software, even today in industry, they do the simulation, they based on tooling reliability, 90% and 99%, the robotic reliability, they're doing the simulation. However, in the plant, there's another aspects not considered, the downtime, is the conformance of the product quality. In a new plant, especially during the launch, there are lots of tooling adjustment. The product, a lot of variability, the product may not be meet the tolerance. In this situation, they shut down the machine. Even the machine works, but they shut down the machine to do the adjustment to make sure the quality is good. So in other words, the product quality also leading to downtime, and these aspects is not in the simulation software when you do the throughput simulation. So even more important, we found out the tooling degradation really impact on the product quality. Tooling become worse, the quality become worse. That makes sense, right? And also, the product quality has a large variability, will leading to the tooling degradation much faster. So the product quality also impact on the tooling reliability. There's a quality reliability co-effect, and this co-effect is not considered in the reliabilities in the system throughput simulation. If you go to industry software today, you can check if they have it. I think our sponsor added this module to the company's simulation software, but not publicly available in the commercial software. So that QR code effect is something I'm going to discuss further in this one. So is there really QR code effect? So this one is 1 year's production data for the quality and the tooling problems that we recorded. And overall, we found out about 72% of a product quality problem is due to the tooling. So tooling is the cause leading to the quality of the problems. And also about 44% of tooling failure, broken, significant wear out, is due to the part has a large variability, large variation. So this real data indicates the quality and the reliability indeed has co-effects. So for multi-stage manufacturing systems, the quality and the reliability has chain effects. So basically, if you look at me, so assume I have a tooling parts, casting parts. I want to drill a hole. So if incoming the tooling casting parts has a large variation, the hardness, the material is not uniform. My drill this hole will wear out much faster compared with uniform the material. So part quality leading to my drill has a different degradation rate. So right now, if my drill is worn out, not perfect, when I drill a hole, the hole is not uniform wall. We have like twisted the wrong dimension. So if the hole has the wrong dimension, I go to next stage, is make a thread. So the hole quality not good. My taper will wear out much faster or broken much easier. If my taper wear out, I make a thread. The thread will not uniform, will be bad quality. So basically, as this slide shows, in multi-stage manufacturing, early stage tooling impact on the quality pass to the next stage will impact on tooling of next stage. And then that the quality, reliability, chain effects. So this one is the QR chain modeling issues. So here you can see, really we want to study QR chain, we need two models. One is how this tooling performance impact on the product. The early SOV model is an example to link them together. And also the product quality, how to impact the tooling degradation. So this need another model and to model this kind of relationship. Once we have these two, we can have this QR code effect and as part of the module in the simulation. So we did a case study for the door frame assembly. So this one, the ABCD pillar of a door inner. And on the bottom here shows the assembly process, how this assemble together as a multi-stage manufacturing process. So in this one, we study the tooling impacts, which is a locator. On the bottom, you can locating pin. And also on the far from here, from me, is 3 to 1 locators. So in this one, you can see on this, we have an incoming part quality. Once the incoming part coming in, the bottom 3 blocks shows the tooling worn out can impact on the part quality. And also the incoming parts quality, the dimension can impact on the tooling failure. The combined effects of the quality and the quality effects and also the tooling effects can impact on the machine failure. So in other words, the machine failure means the downtime can be due to the quality, can be due to the tooling itself, and can be due to the interacting effects. So a quick mathematically how this works. Say we say system reliability is R, which is contributed by the quality RQ and the fixture reliability RF. So these two effects impact on the system reliability. The component reliability is information of each of them, and it's a degradation with defined by the parameter lambda, the second equation. And then the quality will impact on this degradation rate, and which reflect by the third equation. So you can see this delta H is variability. If variability is large, the degradation rate will be larger, will be bigger. And also the reliability in terms of quality. The quality has a variation. If the quality variation larger than the tolerance, that indicates the machine failure. I mean, the machine failure due to the quality issues. So if we know the variation of the product, we know the tolerance, we can translate into the probability. And we have M features, we can get the RQ. So this is the basic concepts, how we model this quality, reliability, and combined effects. So in our simulation study for this door inner assembly process, you can see on the top, this is reliability only. It shows the system is pretty reliable. In fact, this is the results from the commercial software simulation with the tooling, the system reliability. The second one, B here, is the reliability, but considering quality impacts, but not the reliability, QR chain effects, multi-stage QR chain effects. So you can see the reliability is worse than the reliability only. The bottom one is reliability considering quality reliability chain effects. So this one reflects the reliability is much worse. And in fact, the plant conditions is truly reliability considering quality reliability chain effects. So you can see the commercial simulation is far away from the reality. So this concept, we also did further study on different applications. One is study specific for drill effect, I said early. The drill, incoming parts impact on the drill quality impact on the hole, and the hole impact on the threads. So in this particular process, we develop a model to reflect the quality impact on the reliability, reliability impact on the quality, both sides. And then doing the prognostics, you can see the bottom two blocks. On the far right, far left in the front view, that one is conventional methods. On the right is our methods. You can see our proposed methods has a much better prognostics prediction results. And also, we studied real projects with auto company. In the auto company, they have this particular one use cell manufacturing. So they have one station like this components with 1, 2, 3 to M. They are doing exactly the same job, the equipment. The parts come from the left, go through this one, and to the right. The current practice over there use a gantry to drop the parts. They drop the parts to the first available on this component 1, 2, 3, this machine. And then go to next one. The first available means they have no planning, just first available. As a result, they may make the machine or several machines broken at the same time. If these components 1, 2, 3 broken at the same time, the whole production line of the plant will shut down. So the ideal is they have a limited number of maintenance persons. They want the machine in this station, M components, 1 or 2 doing the maintenance, others go through further. And the next cell, multiple stations, 1 or 2 of them broken, doing the maintenance, others going through. So in other words, ideally, these components 1, 2, 3, and so on, they shut down systematically, have enough maintenance to do this, rather than randomly and suddenly has a special failure, most of them shut down. So by using QR chain effects, we model the relationship. We can allocate a certain machine, more task, and more tasks means degradation faster, or less parts means degradation slow. We can control the degradation rate of the machine, so we can purposely group the machine downtime for different stations. By using this concept, we avoid the unexpected downtime of the system. So that's the idea of this. And implement our methods is much more effective to improve the overall throughput and the maintenance crew. So to summarize this talk, I say multi-stage manufacturing process very common in production system, and there are the quality reliability chain effects in that kind of modeling. If we want to do the reliability and the prognostics, we need to study the quality reliability interaction effects. And in order to do a good job, it really need interdisciplinary research and education. Thank you.
Thank you for Professor Zhang Xi. Yeah. we have the time for just one question. Is there any question? We can discuss this topic in panel discussion. Thank you. Yeah. Thank you for Professor Jajunsi. Yeah. Now, yeah. Oh, why don't you have a short break? Yeah. Okay. Yeah. Just 5 minutes or 10 minutes. 5 minutes. Yeah. Okay. We have the 5 minutes break. Yeah. Okay. Thank. Okay. Professor Tony Young. Are you ready? Yeah. Okay. Yeah. Let me introduce the Professor Tony Ng, Bentley University, and his topic is degradative models and related application in reliability. Yeah. Everybody, welcome to Professor Tony Ng. Yeah. Okay.
Thank you. Yeah, thank Professor Bay and Professor Chui for organizing this. And it's my honor to have a chance to share some of my research work over here. In the previous talk, you heard about degradation a little bit. So in this talk, I will focus on degradation, how we can model degradation data, and what we can do to answer problems in reliability. So first, I want to acknowledge my collaborator in these projects, some of my former students. So this is the outline. I plan to give you an introduction on what is called degradation data and give you some example. How does that relate to lifetime data? And also, you heard about PHM, so prognostic and system health management. So how degradation data can be used to help us in PHM. And then I'll talk about the degradation models, some basic ideas. This part will be the most mathematical or technical, but I'll down-tune that and just give you an idea and what we can do. I'll focus on the applications, what degradation models can help us to do, and what problems we can, or what problems and that in reliability we can answer. So some obvious application like battery, and you see network robustness. So I'll show you how this kind of model can be used. And if I have enough time, I'll also show you an application outside reliability context in pharmaceutical industry. And then I'll end that with some extensions and challenges. First of all, what is degradation? Yeah, you heard about that term in the previous talk. Things are degenerating in engineering and sciences. So a system reduced in the performance or reliability gradually is a degradation process. Unfortunately, human is an example. When you get to my age, you will know we are degenerating. So things are getting worse and worse. So one example that I'll use over here is LED light bulb. So I think all of you know what is LED light bulb. When you go and buy one, when you look at the box, it may tell you that the light bulb can last for 10 years or even 20 years. So clearly, they don't collect information. They don't go and test the light bulb for 20 years and then give you that information. So how they can tell you that is based on degradation data analysis. So they collect the degradation over time, what we call quality characteristic related to the lifetime. So over here for LED light bulb, as an example, light intensity is the degradation characteristic that we are measuring. So when you start, the light bulb is great. But after 1 year, the light intensity will drop, so and so on. So based on that information and suitable modeling, we can go and predict the lifetime. And I'll show you more example. So instead of collecting lifetime data in many situations, we cannot go and collect lifetime data. We cannot exactly measure when the item or the product will fail. So we collect something we call degradation measurement to help us to do the prediction. So for if a cumulative degradation characteristic related to lifetime can be observed, then we can use that information to help us to answer reliability problem. So now, how does that relate to PHM? PHM, you may know that that's important in reliability engineering, because if you can prevent failure, that's good, because failure sometimes can be a disaster. Like a good example will be like nuclear plant. If that fail, that will be a big problem. So you want to avoid failure. So PHM, we can use the degradation measurement to help us to see, for example, whether we should do a replacement of the item, the unit, or the component, or go and repair that. You don't want to wait till it fails. So when there are application in different area of health monitoring, so degradation data is important. This is an example. You can see the data that we collect. This is a railroad crack. You don't want that railroad to break. But the crack size will tell us some information about how long will it take for that material to break. So we are collecting data at different time points. We measure the crack size, and the crack size will keep increasing until a point that it breaks. So the point it breaks, we call it a threshold. We use C to denote that. The time it passes, the degradation path past this point, is the lifetime of the unit. So clearly, at certain point, if we can go and predict how much longer it will take for the material to break, then we can do something to avoid the failure happen. We can go and replace, or we can go and repair. So degradation data is collected to assess the lifetime information and reliability information. So we need something called quality characteristic related to the lifetime, and it degrades over time. Sometimes it's quality characteristics because we measure more than one measurement over time to monitor the reliability. So we collect degradation data to assess the product lifetime and for PHM. So we can calculate a lot of things. Like one example is the time at which 100 times P%. For example, if I want to know what time 10% of my products will fail, that will help us to determine what is a good warranty policy, and also estimate the warranty cost. And other things we estimate is like the mean lifetime, mean residual life, and remaining useful life is in particular useful and interest in practice, because we want to answer the question at the time we do the last measurement, how much longer the item can last. So some examples, LED light bulb or lighting, laser, battery is another one. I'll show you another example. And the last one you see at the corner, you may not see the small word over there. Do you know what that is? That's like a light. But what that is for? One of my students who graduated, after he graduated, he went to Federley, the lace strips. That's the knife to cut potato chips in the manufacture. They actually go and study how long it would take for this item to fail, because they don't want that to fail. And Professor Z mentioned, right, the production, the tools will fail. So this will help us to monitor how long will it take for that knife to fail, so we can do replacement, we can do repair. So mathematically, we are interested in measuring at different time point. So that's the notation xt. At different time point t, we measure the degradation. And we want to know when it will pass the threshold c. I'll show you another example. The crack size is one example. Passing through a certain point, that is a failure. One example, that's actually my phone screenshot. I use iPhone. So you can see that if you go to Apple Store and ask, should I change the battery? They will tell you this information. If your charge capacity drop below 80%, they will recommend you to change the battery. So that's actually, if you check your phone, you can see that charge capacity. That's the threshold, 80%. And on this graph, the last graph, you see different DOD. So that's like a covariate in the analysis. DOD is depth of discharge. So if you discharge your phone 20% or 80%, 100%, that will make your the lifetime of your battery different, okay? So discharge that 100% will make the life much shorter compared to you discharge that only 20% and then you recharge it. So we can answer questions like this if we collect degradation data and do suitable analysis. So two major approaches. So now that's the mathematical part, but I'll try to make it short, just give you an idea. The very basic model, there are a lot of generalizations that we have done and other people have done also. So two major approaches to model this kind of data. One is called general path model. We are modeling the degradation path as a function of time. And you can include whatever covariates like this depth of discharge or other like temperature include in the function. Another approach is called stochastic process modeling approach. Instead of modeling the whole path, we are modeling the difference in between two degradation measurements. In other words, it's the increment of the degradation. Like the crack size, we measure how the crack size increased from the last inspection to the current inspection. So that's another approach. So I'll skip the mathematical details, but give you an idea. This is the general path model. You can include parameters that are related to the unit itself, because each unit, they may have variation. Each unit may degrade in a different rate. And some parameters, they are related to the whole degradation process or other covariates. And we can even make it random, so random effect model. So that's called general path model. And another approach, so I'll skip this. And another approach is the stochastic process approach. And one of the many stochastic processes that we can look at is the Levy process. It's a long, proposed long time ago by Paul Levy. So that's a very simple idea. Instead of talking about the mathematical property, I want to tell you what does it mean? What is that infinitely divisible? Basically, it's telling you that each increment, they follow the same distribution. They follow the same probability distribution. They have the same behavior. And if you add them up, they should follow the same distribution, just with different parameter. So that actually makes sense in this stochastic process approach. So there are different Levy process we can look at. So we are looking at the delta xt at different time point in between the two time points, the increment. So over here, if we assume that distribution is a normal distribution, then it is called Wiener process. If we go and assume I'll skip the details, the path will look like that. It can go up and down because normal distribution can take positive and negative values. So the degradation path is not strictly increasing. So to model like crack size, because the crack will not combine that back, right? It's just growing in one direction. So this may not be suitable. So there are other models like gamma or inverse Gaussian. So I'll skip the details, but just show you that it's this kind of model. We can model the increment of the degradation path. And there are other degradation model. What I told you is just very basic, but a lot of generalization, like we can include randomness in the process. Each unit may follow a different distribution, and we can accelerate the degradation process. So we can increase the usage rate to increase the degradation process. Because, for example, the LED light bulb, even you do it by using measurement based on degradation, it still takes a long time. You don't want to wait till 3 years to tell people the light bulb can last for another 10 years. So you want to increase the rate. So you either increase the usage or increase like some factor, temperature, or the voltage to make it fail faster, the degradation rate increase. And you can incorporate other factor in the model to make it more close to reality. So what I told you here is just the basic, but a lot of generalization to make it closer to what we observe in real life. Now, I want to talk about applications. Here are just not inclusive lists of work. I highlight those that I want to talk about, like discharge capacity of lithium-ion battery. But I want to focus on like network robustness and reliability, how this kind of model can be used to answer the question and the objective. I told you it can be used in other areas, not just in engineering or in reliability. We can apply that to biomedical science. Like people measure ACE, that CD4 cell will keep decreasing. So how that process can be modeled. And another application is we have done is drug dissolution. So when you test two drugs, you want that like a generic drug they produce, they want to make sure the rate that dissolve in your body, that can be viewed as a degradation process. They want to make sure it's the generic drug and the original drug, the dissolve rates should be similar. So they need to go through this test, at least in US, when you propose a generic drug, they need to go through this process. So how this model can be used over there. So for the LED light bulb and lithium-ion battery, the main objective is to tell when it will fail, the remaining useful life, how much longer that item can last. Can we predict that? And for network reliability, we are trying to answer the question, evaluate the reliability of a complex network. I'll show you some examples of what complex network means and how we approach the problem by using this kind of degradation model. And if I have time, I'll talk about the application in pharmaceutical, the dissolution profiles. So this one is more obvious. You encounter that. I show you the battery on the iPhone, and you see electric car. Now they use battery, and if you have an electric car, you can have the information on the screen showing you that every time you charge, recharge, how your battery, the charge capacity, or other information related to the battery. So based on those information, the information like those quality characteristics, we want to answer the question, how much longer we need to replace the battery? Should I replace now, or my battery can last for another year, so I don't spend money to replace that now? So the models that we develop can answer this kind of question. And the answer we provide, not just a point estimate, we can have an interval telling you within that range, we are confident that, well, your battery can last for that long. So with that information, you can tell people with an interval, and they can decide whether they want to replace the battery now to avoid it come to failure. So that's a typical application in battery testing and usage. Now, network reliability. So I'll just keep it brief. I'll skip the mathematical details, but tell you what problem we are dealing with and what problem we can provide answer to. So, like different power grids, they are networks. We want to ask the question, which network is more reliable? And if you are the one that build the network, you are building a power grid network, you want to ask which network is, which way we connect those nodes, we call it like a power station, and the user. How can we connect that to increase the reliability under attack? Okay, attack can be intentional, or it can be due to weather. If that is a storm, so some of the power station may go down. So how we can build a network that is more reliable? Other questions I search up, TOS is the one used in Korea. So PayPal or WeChat Pay, those are P2P payment network. So how we can evaluate the reliability of the network? If the server is down, then you cannot use it, then it will create issue. So how we can use degradation to answer the question. And that is cybersecurity problem and related to insurance. Insurance company, they are interested in this because they don't know how to evaluate. That network is more reliable than the other network. How can the insurance company create a policy? So those kind of questions we can answer. And other example is email network. This is an email network, and we actually use that as an example in our work. So we are using the idea of connectivity. If we can have a way to measure the connectivity of the network, then what we got is under attack, that connectivity will decrease over time. When I say time, it's the rate that you remove the nodes when you are under attack. So we can create the path like that. Is actually like degradation data. We can go and compare different networks. Like here, we have an example comparing 3 email networks. Which one is more reliable? So if you are the one doing the attack, that can help you to answer the question, which way I attack the network will be better? Or in the other way, how can I build a network to avoid the attacker to attack my network? So we can answer questions like this. I skip the details and just show you the result. We can come up with an answer. This email network degrades slower when it is under attack, which is a good thing. So in this sense, we can use this kind of degradation model to answer questions in network reliability. And I'll just keep it brief. This is a pharmaceutical application. So I told you that the drug dissolve in your body. They actually go and measure. They have a machine to do the test. They put that into some solution and then measure after 1 hour, after 30 minutes, how the drug dissolve in that solution. So we collect data like this, and we found that that's like degradation. After 5 minutes, 42% of the drug dissolve. After 30 minutes, about 60%, so and so on. It's like a degradation process. We are comparing the new drug to the original drug to see which one degrades faster. So we can apply this kind of model. So it's a simple idea, but a lot of generalizations and also a lot of applications. So there's some challenging that we are dealing with. For example, change point. We observe that a lot of data is showing a change point, or in battery, in this discussion, we have the battery. It actually has two change points. 80% is one, another one we observe in the test is like 20%. So how we can detect that and model this kind of data is one of the challenges. And degradation model for complex system with or without random shocks, like multivariate, I mentioned that we may measure more than one degradation characteristics. Load sharing, when one unit fail in the system, the other items, they need to share the load. So how we can model that? So dependency between different components, all this like involving human factor in the degradation process. If you are interested in this topic, several years ago we edited a book and there are a lot of good papers in that. If you are interested, and here are some review papers that you can refer to if you are interested in this modeling for degradation data. Thank you.
Thank you for Tony. Yeah. It's better to ever discuss panel discussion rather than get any questions. So thank you, Tony. Yeah. Last speaker. Yeah. Professor Manoli from the Education University of Hong Kong. His topic is the Bayesian inference for defect rate of one-shot devices. Please welcome to Professor Manoli. Yeah.
Okay. Thank you, Professor Bear, for organizing this open talk and also inviting me to give a presentation here. It is my honor to share one of my recent work in Korea. And so actually, Professor Bear is a very kind professor, introduced many research topics to me, and I usually work on the technical part. And this is one of the examples. And in this, this is a joint work collaborating with Professor Dr. Shen and Professor Bear. And so in this study, we consider a situation that having a normal device and also defective device. And we assume that for normal device that follows absolutely continuous lifetime distributions like whiteboard distribution, gamma distribution, exponential distribution. So we assume that those normal devices can work for a certain period of time. And for a defective device, we assume that the lifetime is equal to 0. So it means that such kind of device doesn't work at any time. And so in this study, the objective is to estimate the defect rate of one-shot device. And what is one-shot device? And it is a device that can be used only once and it gets destroyed after use. So we can inspect one-shot device only once. So the analysis of one-shot device is really challenging because we have very limited information of the lifetime. So we don't observe the actual lifetime in the analysis, but we only obtain either left censored or right censored data. So it is a binary data set. For example, you can see vehicle airbags and missiles are examples of one-shot device. And also in this study, we consider a more general situation that involving master data. So what is master data? So we assume that participators can determine whether a failed device is originally defective or normal after a careful investigation. But however, in practice, practitioners have a limited time and they may not go through all the failed device. So actually, it means that the root cause is not identified for some failed unit. So we have some master data. So in this study, actually, there are 4 possible outcomes in the collected data. So as you can see that, so if we look at the one-shot device, so we may have so some device passed the test, but some device failed the test, but the practitioner may not have enough time to identify the root cause, so we have masked data. And also for some failed device, we can identify the device is defective or normal. So totally, we have 4 types of device in the data set, and we can find the number of device for corresponding type. And also we can calculate the likelihood. So this is a motivating example that was provided by Professor Bear. So this is return spring data. So as you can see, totally there are 10 testing groups. And for each testing group, the 10 devices were inspected at a particular time. And so this is for, here, the first row is the first testing group. So 10 devices are inspected at 24 hours. And we record the number of surviving devices, masking devices, defective devices, and normally failed devices, and etc. So you can see that in this data set, we only identified 2 defective weights, and totally there are 100 devices tested. So you may think the defective weight is about 2%. But however, we have some masked data. So it means for this data set, we find failed device, but some of which may be defective, some of which may be normal. So we actually, how do we use this information to have a better estimation of the defective weight? So we may consider maximum likelihood inference. So it's a very typical approach. But when the sample size is really small and the defective weight is very low, so the number of defective devices identified in the data set is very likely equal to 0. And in this case, the maximum likelihood approach may fail to find a reasonable estimate. So we may incorporate prior information. So the Bayesian approach is an alternative method for estimating the defective weight. Now, however, when we adopt the Bayesian approach, the posterior distribution may not have the closed expression form. So Metropolis Hastings algorithm is usually adopted, but this algorithm is heavy computation. And so in our study, we try to avoid this heavy computational burden. And how? Actually, when we carefully select the prior information, so we can determine the posterior distribution in a closed form. Like here, we assume that the defective weight for a beta distribution, and the failure probability is more the prior is modified from the beta distribution by multiplying the derivative of the CDF. Then we can find that the posterior distribution has a closed form expression, and capital B is the beta function. So, and furthermore, we can determine the posterior mean of the defect weight. And so the formula is very meaningful because, as you can see, ND is the number of defective device, and K is the total tested device. So ND over K, so you can consider this is defect weight. But when the sample size is small and the defective weight is no, then N is equal to 0, then we can incorporate the prior information CI and DI star into the function. And what is S? S here is the number of defective device mastered in the data set. So, and it ranges from 0 to MN. So it means that we consider all the possible outcomes to estimate the defective weight, and also we put difference rating for different possibilities, and then we come up with the overall defective weight estimate. And how we set up how we determine the posterior informations, like here, if we believe that the defective weight is equal to 0.01, we can set CI star equal to 1 and DI star equal to 99. So then CI over CI star plus DI star is equal to 0.01. Then we can combine the collected data and the prior information to estimate the defect weight. And so as you can see here, we have multiple testing group, then we can combine all the defect weight for each testing group and then come up with the overall defect weight. So this is a new base estimator. So let's go back to the motivating example. And so you can see that here for the first 3 rows, so we can estimate the defect weight by using the Metropolis testing algorithm with different distributions. So you can see that the estimate range from 3.69% to 4.41%, and the computational time is about 10 seconds. But when we compare this result with our new base estimator, the estimate is kind of robust. So it's in between 3.96% and 4.1%. And the estimator is the algorithm is very efficient. So we calculate the estimate less than 1 second. And here, I would like to share some of the papers that relate to this work. And that's the end of my presentation. Thank you.
Thank you for Professor Van Orling. Yeah. Now we have the panel discussion. Before arranging the floor, so we have the 5 minutes break. Yeah, you can take a rest and take a coffee, please. And then we can start a panel discussion 4:55, right? Yeah. Okay. For invited speakers, come to the floor. So we have the panel discussion time. And first, if you any question, you can freely ask your question. Yeah, to related speakers. Yeah. Today, our topic is the PHM and reliability engineering for fault diagnosis and predictive maintenance of battery and manufacturing equipment. However, first, if you don't have any questions, so I can ask a question to Professor Ji. You give a speech on public and private human health care, but PHM for human is maybe similar to PHM for manufacturing equipment or battery. But what is the similarity or what is the difference between human healthcare, human PHM, and equipment PHM? Do you have any idea?
Yeah. Okay, thank you. Yeah, there are differences, but for human it is more challenging because for human there are a lot, especially actually. Remember I mentioned that we are currently focusing on the older adults. Okay, I mentioned because it's the importance of the application because there's a much bigger consequence or impact to the health of the older adult when they have the health problem. So there's only one reason. There's one more reason. That is because for older adult, you could collect the data you collect may be more accurate than the young adult or the young people because you think of the young people, they do so many more things than an older person. Because the older person may just stay home, right? Watching TV or they stay there. So the data, we call it the noises of the data you're collecting about the health are much more noisy for young people. That's why although most of you are wearing Apple Watch, but it's much harder to predict, okay? Because the younger people, they tend to have a lot more activities. They will have, including the activities data, including the environment data. They go to a lot more places. So that the data involved for predicting the health problem for the younger adult will be much more challenging than older adult. So that's at least that's one motivation why we focus on older adult. So for the same thing, for human, there's a lot more noises comparing to the equipment, okay? Because in manufacturing equipment or the battery, okay, so manufacturing a little better because because manufacturing processes and all the equipment have been around for a long time. We collect very good data for the equipment, manufacturing equipment. For batteries, in the lab data, they are a lot easier because they are much less noise. But for the field data where you actually, if your electric bus or electric car, then you collect the field data, real-time data, there will be a lot more noises, okay? But still, for this type of application, there will be much less, comparing to the human will have much bigger noises than the equipment. So that's a major difference. So that's why the human health will be a lot more challenging for application for the manufacturing equipment.
Yeah. Professor Jansi, I am very impressed with what you mentioned, the QR chain, effect. So, in my experience, engineers just consider any product quality, and they take action to improve product quality, but they usually they didn't consider any the tooling quality, because if a tool is degraded, maybe quality will be also degraded. But they just consider the product quality, engineers the quality. However, so when we replace the tool more frequently, it costs more cost, more money. But we need to find out is the best replacement time. But is not quietly studied in this field, reliable field. So, what do you think about tooling quality and product quality? Also, what do you think the best way to find out the optimal replacement time for manufacturing tools?
Okay, it's on, yeah. Okay, I think like this way, basically the tooling company, the equipment company, more like design the tooling, maintain the machine to the target, means the engineer specifications. When the OEM buy a machine from the tooling company, they give the engineer specifications on the tools, on the equipment, and so on. So the maintenance really try to meet that kind of engineer specification. So that's a typical practice. However, in a manufacturing system, the ultimate goal is maintain high throughput, no downtime, hopefully, and maintain the high quality of the product. So in this sense, really the product quality and the throughput is the most important. The engineer tolerance for the machines, of course, very important, especially when we design the machine, we purchase the machine. However, after run certain time, we have better understanding. We should really link the tooling performance, reliability, degradation with the product quality. And so when we do the tooling replacement, we should consider not only the engineer specifications, but also what's the quality delivered by that kind of manufacturing system. That's one thing. Another thing is because of QR chain effects, quality, reliability chain effects in multi-stage manufacturing process, even the tooling company, even the tooling itself, how to design the engineer specifications is not perfect. In the beginning, they don't understand how this quality and the tooling interact. So by continuously monitoring, modeling, and measure the quality and the tooling conditions, they can leading to better QR chain model. And this QR chain model not only leading to better tooling replacement, tooling maintenance, degradation, but also leading to next generation product design. I think that kind of iteration is very important. If we neglect or ignore the quality reliability chain effects, that's a very important aspects missing in the manufacturing company, manufacturing systems. So that's why I come here. I try to promote this idea and say more people from reliability society and the quality society should really work together on this one. And also, I want to say this is not trivial. I just say why not trivial. The tooling has a degradation in the stochastic process. The quality is degradation is another stochastic process. And these two have interactions. So two stochastic process interaction. And then I have a QR chain effects. I'm talking about the multiple tooling in multiple stage, multiple quality in multiple stage. And then that kind of a multiple stochastic process interaction, you want to get a good model. This is a mathematical fundamental research. It's not so easy to solve. Okay.
Yeah. When I consult the manufacturing company, they just ask to give us the data from tooling machine company. Tooling machine company using sensors, they collect the sensor data, but they don't want to provide the data. They don't open the software. So manufacturing company using sensor data, and then they can detect the optimal reference time, or they can use the data. But tooling machine company don't provide the data, sensor data. So at the time, how manufacturing company responds, or they ask, or they just take another action. What do you think about that? Yeah.
I think I'm kind of lucky. In that time, we have an auto body consortium. Basically, is big three with their suppliers, and variation reduction is a common goal for all of them. How to reduce improve quality, reduce variability, and because the automaker is a big boss, so they can dictate to the tooling supplier to say, okay, we need this kind of information. Tooling supplier further dictate their supplier, like locating pin, what kind of a coating. So they have, basically, they kind of open to us. And also, we have students from the university work in the company daily on the variation reduction. So we know what are the root causes, what are the quality level, and also for the given locating pin, something wear out, we know who is the supplier. So we go after them. And because of the support from the, I would say, the CEO president of auto company, they ask the supplier to work with us. That's how we can work on this one. We work on this one for at least more than 10 years continuously. That's how we get the information. And also, we cannot share any data from one automaker to another one. Absolutely no sharing. So each automaker and their supplier will collect the data independently and only keep in the house. And we work with each of them, but absolutely no data sharing.
You mean through the close relationship between manufacturer and suppliers, so they can collaborate together and then get the data and share the data, so to improve the quality. Yeah.
I think it's because of share the common goal, and from the automaker, I don't mention the company. In fact, each of them, automaker from the big boss, they think that's very important. And then they dictate down. It's not close relationship only, but also because of the people in charge from the big boss say you have to do it. And then they ask us, do you have the information? Do you have the support? And then most of the time, yes. If we say no, some other push will get them work.
Oh yeah. Okay. Yeah. Yeah. Professor Tony and Manolin, I have a question. So I studied degradation data when I PhD student 20 years ago, but in real life society, degradation data analysis is very common, well studied. But in Korea, many engineers are familiar with analyzing lifetime data, but they are not familiar with analyzing degradation data, because when we analyze degradation data, we need to any algorithm, for example, optimization algorithm to find out the maximum likely estimate. But there is not common commercial software to analyze degradation data. That is the reason why in Korea many engineers deal with the lifetime data rather than degradation data. At the time, do you have any idea to use and to more often analyze the degradation data in battery and sensor data? Do you have any idea? Yeah.
Well, I haven't seen any specific software that can solve all kinds of problems. Yeah, that's something we can work on. Yeah, to develop software or algorithm that can solve a wide range of problems. Yeah, there are individual software or packages that you can use to solve a particular problem, a particular model. So that's something we can consider, and yeah, to develop a software. I have seen some commercial software like Minitab. I think they have some algorithm to solve part of the problem. JMP also, yeah, by SAS, they have developed some point and click system that you can answer some of the degradation data analysis problems. Yeah.
But for example, SAS and Jump, they provided a limited model of degradation, limited degradation model. So, but degradation data, there are so many kind of degradation data, right? So there is, I think, problem to more often or more frequently used degradation data. I think there is a big problem. So at this moment, so our topic is the battery and manufacturing equipment. How can we develop the PHM and predictive maintenance? So at this time, so I ask your idea, your value of comment to improve the PHM and predictive maintenance for battery and manufacturing equipment. So freely you can give your ideas. Yeah.
Thank you, Professor Bear. And I think PHM is a really new topic recently. And so there are not many commercial software to do the degradation analysis and also the remaining useful life for PHM. And so this is a reason why recently researchers put a lot of effort to develop some new model for new data set and also make it more general. And like what Professor Bear mentioned about the relationship between the degradation analysis and also the PHM, so we can, like what Professor presented in his presentation, so we can first do the build the degradation model and then to predict the remaining useful life. Then based on the information, we can determine when we do the maintenance and what is the optimal time to decide whether we repair the components or we replace it with a new one so that we can minimize the maintenance cost. I think this is really important in PHM. So this is my comments.
Any idea? Yeah.
Well, maybe I can add something. Yeah, because we are actually working on developing maintenance or repair strategy based on degradation data. To tell you, like at the time of the last measurement, we need to make a decision, or last inspection, we need to make a decision when should we do the next inspection, and before the next inspection, should we go and do a maintenance or go and repair the item or even replace the item. So that kind of problem is very useful in PHM. And I also want to address the issue of data sharing that you discussed before. Yeah, in Chinese, that remind me, in Chinese we have a say that a good wife cannot cook a good meal without the rice. Yeah. So without the data, there's nothing much we can do. We can do a lot of methodology or model development, but we need to work with real data to answer real problem. So it will be great if the industry can help us with that, and we are willing to like help to solve different problems. We have the tools, but we need data to help us, and also we need the industry to tell us what are the challenges and what are the problems they are facing. So
Yeah, thank you. Yeah.
Maybe I can say a few words.
Yeah.
I think since you are the president of PHM, maybe something you can lead us to do better for this battery prognostics research. I mean, here, I'm a true believer of data fusion and also true believer of system solutions for a given problem. So talking about the battery, I think the battery life itself is really depending on the material, depending on the fabrication process, and also even the variability during the assembly for different pieces put together. So in other words, the battery itself, the information, fabrication process, manufacturing process, will leading to the life of the battery. That's one thing. Another thing is that the usage of the battery. So what kind of a temperature is in Russia versus in the, in the different locations, the temperature, the environments, the dust, all those kind of things for sure will impact on the life of the battery. So really, the degradation data of battery itself is very, very important information. But only this degradation data alone try to do a good job in the prognostics, I think will be very limited. That's my opinion. So if we want to do a good job, it really need the OEM, the car, if you will say the car battery, really the car company put the sensing information together along the production line of the battery, and all the information, the data collected during the manufacturing process of the battery, and also during the usage. And we do an architecture design for that kind of problem. I know the data collection is the issue, but if we have that kind of architecture design, we know what kind of information we should collect, but we cannot. We can make the assumption on those kind of data follow certain distribution to start with. And then we don't miss this one, but after we do the study, like uncertainty quantification, we know what kind of information is truly more important. We don't have data yet, but we should make efforts to get that kind of a data collection. So through this top-down, I think we can really make the problem solving better. If we only focus on one types of data and work on developer method, that's for sure contribute to the overall big picture. But I think that's not the key point. The key point is President leading us with all aspects of the prognostics and work with this OEM of the car company, even not the battery company. Battery company cannot get additional information of the car usage. I think that kind of design is very important. And to get the expert from those different domain like this, like you are organizing now. And then that will be the start. I won't say, don't say starting point, but really set the basis for continuous work.
Yeah, thank you.
Yeah. So I cannot agree more with Professor Xi's comments, but I wanted to extend it more. I mean, the automobile, again, the concept could be applied to all kind of application, including automobile. But automobile is much harder, okay? And the same thing yesterday when I was giving a talk in Hanyang University, I was mentioning that they are collecting data when you are driving the car, okay? So that will be the field data. But then if you could integrate it with the manufacturing data, like what Professor Xi was saying, then that will be even better. You could do a better job. But the same I was making for human health, automobile, you'll be under a lot more, there are a lot more factors that are affecting it. So rather, I still think battery has a better chance right now, okay? I could share with you the previous research in battery degradation modeling and remaining life prediction. We were using the laboratory data, which they published so many papers already.
Yeah.
They are very famous laboratory data. I mean, you could publish many papers. But like what Professor Xi said, these are not useful because they will not be accurate for the field data. So in fact, recently we got a lot of field data for the electric bus. Okay, you think of that for in the field data, in the lab data, every time you run in the lab, you run it until it finished. Then we start another cycle. So for charging, discharging is a complete cycle. But the real life data, it is incomplete. So then you have a lot more noises. It's a lot more challenging. So that's the first challenges. And the second challenge is how do you link it with the manufacturing data? Right now, we don't have manufacturing data for the battery, okay? But ideally, if you could get manufacturing data, the production data from for each battery, then you could do a better job. But even right now, without the production data, manufacturing data, it's still very challenging to come up with an accurate model for predicting because of the noisy data for charging and recharging in the field data. So there's a lot more that we could do, okay? So that I think there's a lot of potential research there, and I'll be very happy to share when we get more results.
Yeah. Will you give a mic? Yeah. Yeah.
Actually,
Will you use mic?
Actually, that's okay. I worked for a long time work and research work and development in field of structural asymmetry and then progress test management. Then I worked in the agency for the test management. And then I also worked in the research professor in Stanford University for 5 years, 2000 to 2005. At that time, I felt that there are a lot of research work, but there is not much the data, real data. At the time, my colleague and me founded the structural estimator workshop, and then we focused on the instrument, sensor, not analytic tool, not analytics. So right now, and then in the era of digital genes, AI is technology, but main data lab is not much of data, annotation data.
Yeah.
So I think we are how to solve this to get the bunch of data, real data in the age of in the field of edge infrastructure, edge something level mobility or something kind of all things. So
Yeah. Okay, I understand. Yeah. So you mentioned this. Collecting the data is very important, but it is it is not easy to collecting the data and sharing the data. Usually, engineers think that the data is my own. Don't want to share, but first of all, we must open minded to share the data. Yeah, but industry don't open the data. Don't open the data. Is not open the data. Yeah.
the owner of the asset
Yeah.
don't want to open the data to the public.
Yeah. Yeah, there is a reason why this open talk is very short time on the talk, but from tomorrow, so we have the mini conference for PHM and product maintenance. We will share the idea how we can share the data, we can collect the data, and then based on data, we can prognostice and diagnose the status of equipment or battery. So at this time, I'm sorry, but I cannot give you any concrete idea. But we will discuss the topic. How can we collect? How can we share the data in tomorrow? Yeah, I'm so sorry. Yeah, this time. Yeah.
I have one comment. I think the industry will not share prognostic data with the researchers. This should be a fact and will be a fact, because the prognostic data is leading to lots of liability, lots of other consequences. So I think the industry, their product, their data, I think by definition they will not share in public. That's my opinion. I think what we can do, maybe as a society, research society, we can generate some common data with common device, not linked with a particular equipment, particular something, and then use this one as a basis, data sets, to develop kind of methodologies, the methods, data fusion, and then this method will transfer to company. The company inside engineers, and also as a university, we train our best students know how to use this data set, use the methodology, and then the company hire our people, and then do their internal research. In my opinion, that could be the possible pathway to make an impact. If we ask any company to share the data, that's not, I think, not feasible and also not reasonable.
Okay, we have the panel discussion. 30 minutes. Maybe we need to close the panel discussion. Maybe many invited speakers mentioned the importance of data collection and data sharing, but it is not easy. But to improve PHM and predictive maintenance, data, the collection and data quality is very important. So to do so, we need to work together, collaborate together in academy and industry. So I hope this time, this open talk concert will be another chance to share the research idea in terms of data collection and data sharing. Yeah. Thank you for attending this talk concert and listen to this panel discussion. Yeah, I needed to close. Yeah, thank you for your valuable comment. Yeah, ideas. Yeah.